I'd like to start this video with a piece of advice. As you continue to learn the apparent rules of the universe, if you ever become overwhelmed by the complexity of it all, because let's face it, the universe is a very complex place, take a deep breath and focus in on just one aspect. Work your way through smaller, easier to understand concepts one at a time, and before you know it, you'll understand the bigger picture more clearly. In this video, we will start by learning some key terms for kinematics. I will go into detail about these terms because they are very important to learn. Next, I will talk about the equations used in kinematics and which ones are used in a given situation. Then, I will go over an example problem to give you an idea about how to solve them. Before we start, you will need to come to an understanding of a few things. First is that physicists like to work in units called SI units. These include measurements, such as meters for length, kilograms for mass, seconds for time, and others you will learn about as we go. We choose these units so physicists can come to the same answer. Paying attention to units is very useful when solving problems. It can help lead you down the right path, and it can help you check whether or not your answer is correct. If you are interested, this type of technique is called dimensional analysis. The second understanding we need to come to are a few key terms. They are reference point, position, displacement, rate of change, speed, velocity, and acceleration. A reference point, often called a frame of reference, is something we can set to make a problem easier on ourselves. It is generally set to be times 0, wherever the object we're looking at starts, and on graphs like these, the object will be referenced to the origin. This is what makes it our reference point. This graph shows 3 dimensions, but we first need to start with 1. For now, just realize that they are related. Position and displacement are both very similar. They are spatial relationships, but have subtle differences in their definitions. On one-dimensional graphs, these are represented by the variable x. Position is the place the object is compared to the reference point we set, the origin, or in other words, where x equals 0. Displacement is the distance the object is from where it started, which is not always the origin. But since we most often set the reference point as the starting point of the object, position and displacement are in general the same thing, at least in one dimension. Another point to note is both can be worked with as vectors. Now, rate of change. This one can be self-explanatory, but I have seen confusion around the term, so I wanted to include it. A rate of change is a measure that shows how quickly or slowly something changes compared to something else. For our purposes, that something else is time. We look at how position changes in time, or how that position changing in time is also changing in time. If that sounded confusing, just wait, I will explain it soon. In these equations, the line over the V and A stand for average value. These triangles are called deltas, and they stand for change. And these D's are derivatives, which represent instantaneous change for those taking this course with calculus. This brings us to speed and velocity. These are both ways to describe the rate of change of position, or how position changes in time. The difference being that speed will always be a positive value, whereas velocity can be negative. This is because velocity is a vector, and speed is the magnitude of velocity. You likely have a familiarity with speed already. Speed is how fast your car is going, for instance. Velocity is essentially the same thing. It is a measure of how fast something is going, but it has a direction associated with it in relation to our reference point, so it can be positive or negative. Acceleration. This is what I was talking about when I said we look at how position changing in time, velocity, is changing in time. We typically use the units meters per second, or meters per second squared. This tells us how quickly velocity or speed is increasing or decreasing. A higher acceleration means velocity is changing more quickly. Acceleration is a vector, so it can be positive or negative. This means that velocity is slowing down if velocity and acceleration are in opposite directions, or speeding up if velocity and acceleration are in the same direction, even if both are negative. Zero acceleration means velocity is staying constant. It is important to understand the difference between velocity and acceleration. This comes up a lot. Acceleration is the rate of change of velocity. They are related, but are not quite the same thing. Again, I want to stress the importance of understanding these terms. It could prove helpful to revisit these terms, to get them straight in your head. Understanding them will make everything much easier down the road. One final thing before we get to the kinematics. I want to explain this notation a little more in detail, as it may be new to some of you. As I said, this triangle symbol stands for change, and it is shorthand for final minus initial. Final minus initial position, velocity, or time. And what these equations give are average velocity and average acceleration over a given time. The derivatives give instantaneous velocity or acceleration at a given time. Finally, the kinematics. If you are interested in the definition of kinematics, it is simply the branch of physics that looks at motion without regard to the forces that cause that motion. You will learn about forces soon, but for now we're going to focus on kinematics. In one dimension, this is like an object falling from the sky, or a drag car racing down the track. Now of course, looking at these situations in one dimension is an oversimplification, but that is what we are doing, starting simple, and once we come to an understanding, we add more nuance. The type of problems we are going to deal with follow a certain set of equations. There are 4 common equations used to find the values needed when dealing with kinematics. 2 of the equations are derived from the other 2, but it's not bad to have all 4 on hand, as each one can help in different situations. These equations are just tools. Good to have on your belt, but they are not the physics. The physics comes from reasoning through the physical phenomena of a given problem. If you can make a prediction about what is going to happen before even bringing in any equations, you have already done the majority of the physics. Then the equations can be brought in to make your predictions more precise. This is easier said than done. It takes a lot of letting go of previous ways of thinking and accepting that your intuition is likely wrong. But don't get discouraged. I'll walk you through how this process works in an example problem. This first example will be very simple. More complicated ones will come, but we need to start somewhere. We will be dealing with an object falling from the top of a building. A building is 200 meters tall, located on Earth with a gravitational acceleration equal to 9.81 meters per second squared. A person drops a golf ball from the top of the building. Ignoring air resistance, how fast is the object traveling just before it impacts the ground? All the information we need to solve the problem is here, but where should we start? I start by getting a grasp of the situation. Ask yourself, what is going on here? Drawing a picture is a great way to view the problem. We have a tall building, 200 meters tall, with a person on it, and there is a gravitational acceleration of 9.81 meters per second squared in the downward direction, making it negative. Okay, this person now drops a golf ball off the side. They don't throw it, they simply let go of it. Now the ball is falling. How is it falling? Is it falling at a constant speed? Well, no, we have gravity here. Gravity accelerates objects, which means the rate at which it is falling is getting larger. Again, the velocity is increasing, and the acceleration is the amount it is increasing by. Okay, since the ball is accelerating downward, and its velocity is increasing down for the entire fall, it must be traveling fairly fast in the downward direction right before it hits the ground. We want to find the velocity before it hits the ground, which should be larger than its initial velocity. Now that we have a grasp of the situation, we will start to solve the problem a little more precisely. First, we need to identify what we know. Ask yourself, what do I know? In this case, we know that the height of the building is 200 meters, which means our initial position is 200 meters and our final position is 0 meters. You'll notice here, I set my reference point to be the ground. This is a common thing to do. We also know that the acceleration that the ball experiences is 9.81 meters per second squared. We also know one other thing, but this has to be interpreted from the problem. We know that the ball is dropped, not thrown. What does this mean about the initial velocity of the ball? It means that it isn't moving at first. that the initial velocity is 0 right when it is let go. Now we need to figure out what we don't know. We don't know a lot of things, like what I'm going to have for dinner, the time it takes for the ball to reach the ground, or the velocity right before hitting the ground. Only some of these are relevant though, so let's just keep those in mind. Identifying what we are trying to find is the next step. It says right in the problem, what is the velocity right before reaching the ground? It may prove useful to find the time it takes for the ball to fall, but for now we will just keep that idea in the back of our minds. Now comes the question, how can I find what I need from what I have? We know this is a kinematics problem, both because I told you, but also because there is no mention of forces in the premise of the problem. That means we look at our tools associated with kinematics, our kinematics equations. There is no need to memorize these. They are easily available. It's more important to learn how to use them. One important note is that these are only valid with a constant acceleration, like that of gravity. These are the guidelines for how to use each equation. This first one is used when we don't know the distance traveled and don't need to find it. The second one is for when we don't know the final velocity but don't need to find it. The third is when we don't know the acceleration and don't need to find it. And the fourth is used when we don't know the time and don't need to find it. Okay, we know that we don't know the time or the final velocity, but we do want to find the final velocity, so we must use the fourth equation. Now before plugging in the values we have into the equation, it's good to get into the habit of manipulating the equation first, then plugging in the known values. This has two benefits. First, it demonstrates an understanding of what is going on in the problem, but also it can be useful when given similar problems with different values to make calculations easy and efficient. That being said, the only manipulation this equation needs is taking the square root of each side, so that we have v final with no square. From here, it's just a matter of plugging in the known values to find the answer we are looking for. Because square roots can give a positive and a negative answer, we find that the final velocity is equal to negative 44.29 meters per second, since we know from the problem it is in the downward direction. This was a fairly straightforward problem, but I wanted to start with something simple to really break down the thinking process without too much confusion. In later videos, I will go over more complicated problems to build on the strategies I have laid out here. Here is a piece of knowledge candy that didn't really fit into the narrative of my video, but I wanted to share because I find it interesting and it might help you learn to read a graph. Here we have a graph of position as time passes. While this only represents motion in one spatial dimension, we need a two-dimensional graph to represent both space and time. Keep this in mind when you read graphs. These sometimes change, and it's up to you to interpret them correctly. What I'm going to show you is related to this kinematics equation to find position. When initial velocity and acceleration are both 0, our object stays at whatever its initial position is as time passes, graphed as a horizontal line. When initial velocity is non-zero, but acceleration is 0, the position of our object changes at a constant rate, whatever our initial velocity happens to be, which is the slope of our line. Now, when we add a constant acceleration to our object, like gravity for instance, the position starts changing at a faster and faster rate as time passes, because our velocity is now changing due to the acceleration. The further up on this graph the object is, the further it has traveled in a given time. Just an interesting way to visualize how velocity and acceleration can affect the motion of an object. I appreciate you taking the time to watch this video. Please like, share, and subscribe to support my channel. And if you feel you are able, and that these videos are worth it, you can support me through Patreon, crypto, or PayPal. Links in the description.